Hi, this is Gordon Parker from Michigan Tech, and in this video we're going to look at different ways to represent dynamic systems and then also how to analyze their steady-state characteristics. So first let's review transfer functions, and I'll abbreviate it like this, transfer functions. What do we know about them? Well, it's an output variable over an input variable, and they're in the Laplace domain. So a typical example would be a y over u equals g of s, and let's say we had an s plus 2 over s squared plus 7s plus 12. So there's a beautiful looking transfer function. We also know that from a differential equation standpoint, we would set all the initial conditions to 0. So it strictly tells us information about the system's response when there's some type of an input u and all initial conditions are 0. We also know in general about Laplace transforms that s in the Laplace domain, or multiplication by s in the Laplace domain, is like taking the derivative in the time domain. And similarly, division by s is just the same as integration in the time domain. That means that we can have all kinds of fun with transfer functions like the one above. We could multiply both sides by s squared plus 7s plus 12, and we would get this. And so we can quickly go back to the time domain like this. Okay, so now I have two different ways to represent the same dynamic system. Here it is in the time domain, and there it is up top in the Laplace domain. Now, from a terminology standpoint, when we're working with transfer functions, we define what are called the zeros as being the roots of the numerator. Roots of numerator. And its poles are the roots of the denominator. So what that lets us do, going back to this example, g of s is s plus 2 over, well, let's see, we had s squared plus 7s plus 12, and if I factor that denominator, I actually get s plus 3 and s plus 4. So this gives us yet another way to represent this dynamic system, specifically by plotting its poles and zeros in the complex plane. So I'll just draw a couple hash marks here and there. And what we do is we use little o's for the zeros, and so we would have a 0 at, let's see, I'll go z for my zeros. We have one at -2, and then my poles, I have one at -3, and another one at -4. So I would go boom for my 0, boom, boom for my poles. This is yet another way to represent that dynamic system. I could show this pole zero diagram to someone and they would know exactly what my transfer function is up to an unknown constant. And what I mean by that is that this pole zero diagram is for this system, but the exact same pole zero diagram is for another g of s, I'll call it g1 of s, that is, let's say, 5 times s plus 2 over the same denominator. Right, so the pole zero diagram doesn't give us any information about that constant. Now, of course, I can also do pole zero diagrams for transfer functions that have complex poles. So let me do another one. I'll say g of s is equal to, I'll keep that numerator the same. And how about we use this for the denominator? Again, my 0 is at -2, but now my poles I have to get from solving this equation. And actually, before I do that, we give this equation a very special name. This is called the characteristic equation. And sometimes it's denoted as f. So we would say f of s is equal to s squared plus 2s plus 10. So another way of describing your poles is, or are, that your poles are the roots of the system's characteristic equation. But let's go back here and solve for these stinkers. So we'd go S1, 1, and 2. We have two of those roots of the characteristic equation would be negative 2 plus minus 4 minus 40 over 2, which is negative 1 plus or minus negative third square root of 36, which is 6 over 2, so 3j. So our pole zero diagram for this system, put some little hash marks in here, boom, 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 would be, let's see, I have a 0 at negative 2, and I have poles at negative 1 plus or minus 3j, an x there and an x there. Again, I can communicate my transfer function that way or this way. The only uncertainty is that constant that could be in front of that numerator. Okay, so we have several different ways to represent a dynamic system. We have the time domain, we have pole zero diagrams, and also transfer functions. Now let's start talking about the response. And to do that, we need to introduce the initial value theorem, IVT, initial value theorem, and the final value theorem, FVT. What these things do is they give us a way of working with the system in the Laplace domain, a transfer function, and determining characteristics of the response of the system in the time domain. The initial value theorem, for instance, tells us the initial value in the time domain of that dynamic system, and the final value theorem tells us where that system ends up once it reaches steady state. Of course, that means that it has to reach steady state, so it's not always going to be applicable. For instance, if we had a y of t that did this, right? It's sort of this unstable response, grows without bound. It has no steady state. So the FVT, the final value theorem, doesn't apply. And we'll have some conditions that tell us that without actually having to plot the response. So the final value theorem works great for systems that have this type of a response, a nice final value. And so what it tells us is what that value is. Let's say it was 2. Okay, so let's go ahead and develop the those two theorems. So we'll do the initial value theorem first, IVT, and it goes like this. We'll say y at time equals 0 is equal to the limit as s goes to infinity of s times y of s. So assuming that I have some function y of s, I multiply it by s, and I'll let s go to infinity. And this works every time as long as the limit exists. So there's sort of a caveat here. As long as the limit exists. The final value theorem goes like this. Y at time equal infinity is equal to the limit as s goes to 0 of s times y of s. Now, this one applies when all the poles of s times y of s, that thing that we're going to take the limit of, are in the left half plane. I'll write it out. Left half plane. And what this means is if I were to plot a pole zero diagram of s times y of s, making sure I do all the cancellations that are possible, my poles have to lie over here, where this is the real and this is the imaginary axes. So let's do a couple, or at least an example, to illustrate these two things. Let's say I have this transfer function, the same one that we've looked at before, s plus 2 over s plus 3 times s plus 4. And what we'll do is we'll analyze the initial value theorem and the final value theorem for two different cases. A, we'll we'll let u equal 1 over s, that is a step. And b, we'll let u equal 1, that is an impulse. Why don't we do b first, actually? So we'll start from the bottom up. So here's our b case, and let's do the initial value theorem. Okay, so when capital U is equal to 1, then y of s is just s plus 2 over s plus 3 and s plus 4. And the initial value theorem says that y at time equals 0 is equal to the limit as s goes to infinity of s plus 2 over, I'll go ahead and multiply this back out again, s squared plus 7s plus 12. And we have to do one more step perhaps to get this limit. What I'll do is divide everything by s squared. So let's see, I'll get 1, 2 over s, 1 plus 7 over s plus 12 over s squared. And so now when I let s go to infinity, I can see pretty clearly that I get 1. So the initial value of this system in the time domain is equal to 1. Very good. So now let's do the final value theorem. And again, we're doing case B where the input is an impulse. And what this says is that y at time equal infinity is equal to the limit as s goes to 0 of s times y of s. So that would be s plus 2 over s plus 3 and s plus 4. Now before I haul off and go ahead and let this s go to 0, I have to check that all the poles of this are in the left half plane. LHP, question mark. Well, I can eyeball that and say yes. So the final value theorem does apply. And when I let s go to 0, it's pretty clear that what I'm going to get is 0. So what this says is that if I hit this system with an impulse, eventually y of t is going to go to 0. Now we can determine that pretty easily for this system, so I'm still working on b. What I'm going to do is check the result we just came up with. My y of s was equal to s plus 2 over s plus 3 and s plus 4. This is when we let u equal an impulse, which is 1. If I do a partial fraction expansion on this, I will get this. And if I now go to the time domain with those two expressions, I'll get y of t is equal to c1 e to the negative 3t plus c2 e to the negative 4t. I don't even have to calculate c1 and c2. I can see clearly that as I let t go to infinity, each one of those terms goes to 0. And so lo and behold, y at infinity is equal to 0. So that's the result we got from simply looking at it in the Laplace domain. And we didn't really have to do all this inverse Laplace transform stuff. That's one of the powerful aspects of the final value theorem. So now let's do case A, where we let u equal 1 over s, a step. When we do that, we get y is equal to s plus 2 divided by s squared plus 7s plus 12. Now, for the initial value theorem, we would go y at time equals 0 is equal to the limit as s goes to infinity of s times y of s. Now, when we do that, we'll get limit as s goes to infinity. This s is going to cancel with that one, and so we'll just have s plus 2 over s squared plus 7s plus 12. And when we let s go to infinity in this case, we'll just get what? Let's see. Oops. If we divide through by s squared again, we'll get 1 over s plus 2 over s squared over 1 plus 7 over s plus 12 over s squared. Letting s go to infinity, we get 0. So the initial value theorem tells us in this case, y at time equals 0 was 0. Now, for the more interesting case, again we're working with A, where u is equal to a unit step, and we'll do the final value theorem. So y is equal to, again, s plus 2 over s squared plus 7s plus 12. And y equal at infinity is equal to the limit, as s goes to 0, of s times y of s. So y at infinity is equal to the limit, as s goes to 0, of s plus 2 over s squared plus 7s plus 12, and that is 1/6. Interesting. Now let's go ahead and check that using inverse Laplace transforms. I'm just going to take that y and expand it into a partial fraction expansion. c1 over s, c2 over s plus 3, and c3 over s plus 4. Now, when I go to the time domain, I'm going to get c1 plus c2 e to the negative 3t plus c3 e to the negative 4t. These two terms, as time goes to infinity, do nothing. But this one gives us perhaps a final value, a steady state value. And we can find c1 by going, let's see, that's for this root. So it'd be s times y, and then let s equal 0. So c1 is equal to 2 over 12, or 1/6. It all checks. It's beautiful. Okay, this example actually has a lot of meaning for the last thing that we're going to do here, and that is looking at a thing called the DC gain. The DC gain. So it's the gain of your system when the system is at steady state, is one way to think about it. A more formal way to think about it is that what you do is you provide the system a unit step input. So you have some transfer function, y over u is equal to some g of s, and you let u equal 1 over s. That's exactly what we did in the previous example. And then the DC gain is the ratio of the steady state output to the input. Of course, the input is just 1, right, because it's a unit step, so that's kind of boring. So really all we have to do is get the steady state output. Well now, of course we're going to use the final value theorem for that. And of course this only applies when the system has a steady state when you hit it with a step. So there's a couple things that you have to just check before you go ahead and do it. If all these things check, well, then we can get a nice simple formula that we can use, but you never really have to use the formula if you just remember this. All you have to know is that you hit the system with a step input and then find the steady state response, and then that thing is the DC gain. And it's called the DC gain because once you know it, then you know the steady state response for any amplitude step simply by multiplying that DC gain by whatever that step amplitude is. Okay, so let's go ahead and write down what happens. Right, we're going to use the final value theorem. So we're going to let s go to infinity, and we're going to, of course, multiply it by s. That's part of the final value theorem. And what we're doing is we're taking g of s like this, letting u equal 1 over s. So really it's g over s. Right? When we take this u and put it over here and let u equal 1 over s, we get g over s. Those cancel out, and so now we could just have this formula where we say the DC gain is equal to the limit as s goes to infinity of just g of s. And of course, all poles of g of s must be in the left half plane. And that's exactly the example that we had just a couple minutes ago. So we could do something like the DC gain. Well, let's see. Let's review. Y over u was equal to s plus 2 over s squared plus 7s plus 12. And according to what we just did with that little formula, we could say the DC gain is the limit as s goes to 0 of g of s, which is this. And that's equal to 2 over 12, or 1/6. And they're beautiful. Now, if we extend this idea just a little bit, okay, so if we look at u and y, what this is saying is that if we give the system a step input u, and then the output, and for this case it would be 1/6, but let's say that we had a DC gain of 3, just to make it a little bit easier to draw. If we had a DC gain of 3, maybe the system response does something strange, but eventually it gets up to here, where this is 1 and this is 3. Again, that's not this example. This is an example where the DC gain is equal to 3. Now what this also means, though, is that if I were to hit the system with a different type of input, not necessarily a step, but one that ended up being that same value, let's say 2 in steady state. So this is u and this is 2. What this tells us is that in steady state, my output is going to be 3 times 2, or 6. Even though it's not exactly a step, it achieves a steady state value, which is step-like. In this case, though, with a value of 2, and so now I know, without doing any other analysis, because I know that the DC gain is 3, I know that the steady state response is going to be 6. Fun stuff. The last thing that we're going to do is just take a look at some of these concepts using MATLAB. Okay, so we've been working with the final value theorem and DC gain, and there was a particular example that we've been playing with that looks like, let's see, we'll call it y, well, let's call it g, is equal to, and I'll make a transfer function object out of this, and let's see, we had 1, 2 for the numerator, and 1, 7, 12 for the denominator. Beautiful. And in MATLAB, all we have to do to get the step response is go step g. You'll think about it for a second. And remember what our DC gain was. It was 1/6. And what do we get here? If I click on this and kind of slide it over to there, I'll get an amplitude of 0.167. Yep, that is 1/6. So everything checks out. There's our DC gain. Now, we also looked at the final value theorem when the input was an impulse. So let's do that one in MATLAB. We can just say impulse g, and we'll get the impulse response. It starts out at 1. That was our initial value theorem that we solved for, and that's correct. And then it jumps down, and lo and behold, it goes to 0, which is exactly the final value theorem that, or the final value that we calculated from the final value theorem. So we looked at several different ways to represent a dynamic system in the Laplace domain, showed how we can quickly go to the time domain, but really stayed in the Laplace domain most of the time. Then we moved into the initial value theorem and final value theorem, and then did a special subset of the final value theorem to get the DC gain. And you can always use step and impulse in MATLAB to play around with your systems to check that you've calculated the right DC gain and to assess its response. So again, this is Gordon Parker from Michigan Tech, and thanks for watching.